Hello, let's solve another calculus optimization problem. A cylindrical can is to be made to hold 1000 cubic centimeters of oil. Find the dimensions that will minimize the surface area and hence the cost of the can. This is the third problem in the list that I gave to sections A and B. The problem talks about two aspects of a cylinder, its volume and its surface area, so let's recall the formulas for those. On the right side, a cylinder with radius r and height h. The volume of shapes like this is the base times the height. So the base is a circle with area pi r squared, so you have that multiplied by h, and that provides us with a volume. Now the surface area is really the sum of the areas of all the faces. The cylinder has a circular top and a circular base, so that's why you have double pi r squared, making up the first term the surface area. Now, as for the what we refer to as the lateral side, the surface, the side of the can, you can think of that as a rectangle that's wrapped around the side. So we have to find the area of this rectangle. It has height h, so that explains this factor in the second term. And then the other dimension of that rectangle wrapped around the cylinder is how far you have to go around the circle. So that's 2 pi r. So the second term, the surface area, is 2 pi rh. Now going back to the problem, the volume is 1000 cubic centimeters, so that means you have pi r squared h is equal to 1000. Now the goal is to minimize the surface area. Then if you look at this formula, you're probably thinking, wait, we can always make that as small as we want by making r smaller, then making h smaller. But then you have to take into account that whatever r and h are, they have to satisfy this condition. So you can't just arbitrarily reduce the value of r and reduce the value of h because you need this condition to still be satisfied. So also another issue that you may have observed is that the formula for the surface area is in terms of two variables, r and h. So how can we do our calculus on that? Simple. We're going to use this constraint, this volume condition. We can solve for one of the variables here. Either we solve for r or h, and then we can use that to modify the formula we have for the surface area so that in the end it will just be in terms of one variable. Now we have two options. If we go back to this volume, this constraint condition, either we solve for h. So if we do that, h is therefore going to be 1000 over pi r squared. Okay, I don't know why the okay. So 1000 over pi r squared, or you can solve for r as that's going to be 1000 over pi h, and then the square root, no need to worry about negative square roots because r is clearly a positive quantity. But the thing is, if you're going to use this second formula, you're going to have to put that here on r squared and also here. But the problem is that, well, then you're going to have to deal with a radical expression there. On the other hand, if what you're going to do is use this uh, expression for h and input that into the surface area, first off, you're not going to have to deal with radicals, and you're only going to have to make that replacement here. So overall, I think solving for h and using it on the surface area formula would be so much easier. So now let's rewrite our surface area now as a function of r. How do you know that? Oh, because h is going to be replaced by this r expression. So s is 2 pi r squared plus 2 pi and then r, and then as we agreed, we're going to replace h by 1000 over pi r squared. We just have to clean this up. We could cancel the pi's, and then you have this r and then this r squared down here acting together in tandem. So we have now 2 pi r squared, 2 pi r squared. So what do we have here? 2 with 1000, so you have 2000. No pi's left, instead just a single r. A departure from previous situations is that this time the domain is not going to be a closed interval. Well, to determine the domain, we have to think of the possible values that R can take. Well, clearly R is a radius, so it cannot be 0. And if you look at the only thing that R has to satisfy, it would be this formula that H is 1000 over pi R squared. So R can be arbitrarily very close to 0. That's fine. It's just going to make the value of H large, but that's still going to be within the realm of possibility. And is there like an upper bound for R, a value that R cannot reach? No, actually, if you provide a very, very large value for R, then that's just going to make the value of H really, really small, but overall still within the realm of possibility. So the only condition we could impose on R really is that R has to be positive. So in other words, the domain of the function S is the interval 0 to infinity. So you can't rely on the absolute value theorem, where you have to, after finding the critical numbers, evaluate the function S of R here at the endpoints, because there is no endpoint. I mean, fine, you have 0, but it's not even part of the domain. So, well, our main interest really is the absolute minimum, but for now, I will explain later how to resolve this. Let's find the relative minimum. So we start still with the derivative s prime of r. Okay, s prime of r is 4 pi r, and then that's going to be minus 2000 over r squared. Don't forget to always look for both kinds of critical numbers. For critical numbers, it will make this undefined. Well, that's only going to happen when r is 0 because of this denominator, but 0 is not in the domain. So we only need to consider the situation where this expression is equal to 0. You have, therefore, this fraction, r squared, with numerator 4 pi r cubed minus 2000, and equate this to 0. But then the only way that this is ever going to be 0 is if the numerator is equal to 0. And that's going to happen when r cubed is 2000 over 4 pi. Or in other words, r is equal to the cube root of, that's 500 over pi. Now, what a lot of students would do is stop at this juncture and conclude that, yes, this is the R value that we need that will minimize the surface area. But really all you've done is you've determined the critical number. And we've seen how, in general, not how a critical number in certain situations could actually turn out to be useless. We don't think that's going to be the case here, but your gut feel does not constitute a proof. We have to provide justification that this R value really does provide the least possible value of the surface area. So either you use the first derivative test or the second derivative test. In this case, it would actually be simpler to use the second derivative test because all you gotta do is differentiate your S prime of R one more time. S double prime of R is equal to 4 pi, and then the second term is minus 2000 over r squared, so the derivative of that is going to be plus 4000 over pi r cubed. What we do with the second derivative test is we evaluate that at the critical number and decide if the output is going to be positive or negative. But in this case, fortunately, if you look at the two terms making up S double prime, the first is 4 pi positive, the second is 4000 over pi r cubed. You don't have to know the exact value, but that second term is also going to be positive. And just like that, we then get to conclude that S has a relative minimum at our critical number cube root of 500 over pi. But how do we know that the point corresponding to this critical number is actually the lowest point on the graph? Now, it would then like you to consider the following easily recognizable fact. Just Just gotta move it here. All right, and make it larger so everyone can see. This looks very much like the statement of the second derivative test. So f is continuous in an interval with only one critical value c and I. So except for that, all right, did this extra condition, c is the only critical value in the interval I. So we're going to return to that. And then the two if statements deal with c being a critical number of the first type. So f prime of c is equal to 0. And just like before, we look at the sign of the second derivative. For the first if statement, suppose f double prime of c is positive, so you have a graph which is concave up, so therefore at c, what you have is a relative minimum. Now, we get to conclude that f of c is not just a relative minimum, but it's actually the absolute minimum because of the fact that you only have one critical value. So how do we know that at c, you're not going to have the lowest point on the graph? Because there is no opportunity for the graph to go lower than that. How so? Because if you look at this first figure, all right, on the left the graph is ascending, on the right the graph is also ascending, and the only way for the ascent to be stopped, for the graph to go down, is if there was a turning point, if there was another critical number. But there is no other critical number. There is no opportunity for the graph to stop its ascent, change direction, and go down lower than the point at C. Ditto for the second situation, f double prime of c is negative, so you have a graph which is concave down, so therefore at c you have a relative maximum, but because there is no other critical number, the descent of the graph to the left and the right cannot be reversed because there is no other critical number where you could make that change in direction. So therefore, if we go back to our problem, s has a relative minimum at our sole critical number, and because of the fact that, fortunately, hold on, yikes, okay, my train of thought stopped there, oh yikes, all right, draw, no, 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 all right, so this is the only critical number we have. Where was I? Therefore, s has its absolute minimum at the cube root of 500 over pi. Now we're almost done. We just gotta ensure that we've answered the question. The task really is to determine the dimensions that will minimize the surface area. So what are the dimensions in this case? It's the radius and the height. Well, the radius is this critical number, so to minimize the surface area, the radius has to be the cube root of 500 over pi. And as for the height, we only need go back to this 1000 over pi r squared as the corresponding expression for the height. So h is 1000 over pi r squared. Now, it is appropriate to come up with an approximation for the radius because this is a measurement, so it's just weird giving it as the cube root of 500 over pi. So you have 5.42 centimeters, and then using this r value, you could also approximate the value of h. You're going to end up with 10.84 centimeters. And in case you're wondering, it's actually not a coincidence that h is double the radius because you could use the exact value of r, plug that here into the denominator r squared of h. So you could also end up with the exact value of h, and then you could use those exact values to show that h is actually double r. So yay, these are the dimensions that will minimize the surface area. End of problem. Yahoo!